All right, in chapter 16 we saw binomial distribution, where the expected value is the mean, n times p. The standard deviation is the square root of NPQ. So a small example here, let's say we inspect 1,000 pipes and that the probability of a leak is 0.04. So the expected value of number of leaks would be n times p, or 0.04 times 1,000, which is 40. Note that Q will be 1 minus 0.04, or 0.96, and n times Q in this case is 960. All right, what I just showed here is NP and NQ are both greater than or equal to 10, and so we can approximate this using the normal distribution. All right, so we could do something like, well, what is the probability that you'll have less than or equal to 30 leaks? In other words, if you'll have 30 leaks or less. All right, well, we can do this by using our normal distribution as a estimation, as an approximation to binomial. So solving for the mean and the standard deviation, we get the mean is 40. So I can go ahead and write that the center of our normal distribution is 40. Our standard deviation is 6.17. So I can go ahead and write this would be about 46.17. This would be about 35.8 something or other. Let's see, 40 minus the standard deviation, 33, let's try. 33.803. Okay, and the problem that we were asking here is what's the probability of x being less than or equal to 30? What's the probability that you have at most 30 leaks? Okay, so that's about somewhere over here. We're finding the probability, or the area, to the left of x equals 30. All right, so we have a normal distribution, mean, standard deviation, and we're finding the probability that x is less than or equal to 30. So we'll go ahead and do this in StatCrunch under Stat, normal calculators, normal, and we can find the probability that x is less than or equal to 30. When I plug that into the StatCrunch calculator, I get 0.0533, or about a 5% probability. So you have, assuming that P is 0.04, you have a 4% probability of having a leak at any one pipe. You examine 1,000 pipes, and the probability that most 30 pipes will have a leak is about 5%, or 0.0533. Well, this is actually almost the same as what we're doing in chapter 17, except in chapter 17 we have we're looking at the sampling distribution of proportions. What do I mean by that? Well, proportions, by the way, the sampling proportions are just x out of n. In other words, we expect 4%. We expect that the leaks are going to occur at about 4%. However, and so we take, 1,000 pipes, and we say, and we count how many leaks there were, and let's say we counted 36 leaks. So this is p hat. P hat would be 0.036, 36 over 1,000, and p is the probability for the population. We don't always get exactly 40 out of 1,000 that's going to have a leak. We might get something like 36 out of 1,000. Well, okay, so basically that is one p hat. That is one possible sample proportion I could get if I got n equals 1,000 pipes and I counted the number of leaks. Here, basically, if you notice, we're going to instead of having an x down at the bottom, instead of having we have a p hat. In other words, it's x over n. So I'm now saying I'm going to divide everything by n. Instead of the mean being the NP, it's just going to be P. In other words, for sample proportions, your expected value, your expected proportion is going to be 4%. This is your expected value of your sample proportions, or 0.04. So that's going to be what's in the middle. That's your expected value of your sample proportions, and it's just the population proportion. Same thing here. Instead of square root of NPQ, I'm going to divide everything by n, and what I get is PQ, square root of PQ over n. This is now my standard deviation. This is my standard deviation for my sampling distribution of proportions. So in this case, when we're doing, again, the biggest difference here, we're doing the distribution of all sampling proportions given n equals 1,000. So if I took 1,000,000 samples of 1,000, these are different values of p hat, of the sample proportion that I get, and it would be distributed normally if NP and NQ are greater than or equal to 10, just the same thing as the last. All right, so here our sampling distribution is as follows. It is approximately normal because NP and NQ are greater than or equal to 10. Our mean is P, and our standard deviation is PQ over N. Our mean is 0.04, and our standard deviation is 0.006. So here we're basically saying what's the probability that we get, and if we have, let's say, x is less than or equal to 30, we're saying what's the probability that p hat is less than or equal to 30 over 1,000? Whoops. All right, what's the probability that our sample proportion will be less than or equal to 0.03? All right, so again, we can put 0.03 here. We're finding the area to the left of 0.03, and that's the probability that our sample proportion is less than 0.03, or 30 out of 1,000. I plug that into our calculator, and I also get 0.05. Due to rounding, I got 0.078, etc., but we basically get the same value. All right, so in here, again, the biggest thing to notice here is that we were doing sampling distributions of x. Just x is the number of successes in 1,000. However, on the next page, we're doing the sampling distribution of proportions, and we have that instead of x, we have p hat. This is the sampling proportion out of 1,000. All right, so of 1,000, we're basically, this is like putting percentages instead of x values, instead of successes. But it's the same, pretty much the same thing as we're doing. We're basically just dividing everything by n.